Yeah, the arc-length theorem. I kind of tried to derive this integral for you. Again, that was like a non-rigorous derivation. The actual proof of this theorem requires Riemann sums and partitioning and all that. But the basic idea is Pythagorean theorem. Okay, summing up these increments, that gives you arc length. And the length of each of those increments, which is called a delta S, is again just Pythagorean theorem. Okay, so let's do an example. Let's do two examples. Let's go with the circle of radius A. Okay, so here C, the curve is defined as x equal to A cosine T, y A sine T, where T goes from 0 to 2 pi, and again, A is positive. Okay, we want to find the length of C, which is basically the circumference of a circle of radius A. Okay, well, first of all, we're going to have to use arc-length theorem, so we have to check its requirements. Okay, don't just apply a theorem, assumptions must satisfy. Okay, and that is we want C to be smooth and simple or closed simple. Okay, we already know that this circle is closed simple. It doesn't intersect itself, or it doesn't overlap except at the end points. Okay, so check C being simple. It is. Okay, we know that C is closed simple. Okay, you don't even need to do anything mathematically, honestly, because here T goes from 0 to 2 pi. Okay, so that's that. You want to check for smoothness, and it's better that you check for smoothness, not just because you need to check that the assumptions are met. It's because when you check for smoothness, you have to compute this expression, okay? And that way you have you've kind of solved half of the problem here. Okay, so check smoothness. All right, we have to find the derivatives with respect to t. We have dx dt, which is the derivative of a cosine t, that's negative a sine t, and dy dt, derivative of a sine t, that's a cosine t. All right, there are two things to check. Number one, those derivatives have to be defined on the domain of integration, and they are defined. A sine t, a cosine t, those are continuous functions. They're always defined. Their domain is all reals. So just write it down. Okay, they're both defined for all reals. I don't even need to say, mention the domain. Second requirement, these derivatives cannot be zero together. There should be no t value that makes both of them simultaneously zero. Okay, so one way to go with that is to find the zeros of each derivative and see if there are any common zeros. That's kind of difficult to do. Or you can just sum the square of the derivatives, and that expression should be positive. We'll look at dx dt squared plus dy dt squared. That's negative a sine t. We square that. We add that to a cosine t, square that. Okay. Both of these squares have an a squared. You can take that a square out. That leaves you with sine square t plus cosine square t. And we know that is Pythagorean. So it's 1 times a squared is a squared. Okay. And we know that a squared is never zero because they tell us a is positive. A is the radius. It can't be zero. That's positive, so it checks out. Okay, so again, if there is a t, if there is a t that makes this zero, then there would be common zeros, and that's not happening here. Okay. So Jose is asking, in order for C to be simple. So again, Jose, C is closed simple. It is closed simple. A closed simple curve is a curve that intersects itself only at the endpoints. We call this closed simple. Okay, so a circle starting right there, ending back at that point, where including 0 and 2 pi makes this curve closed simple. Okay, yeah. So the only time C can intersect itself is at the endpoint. That makes it again closed simple. All right, so again, this being more than 0 means that dx dt and dy dt cannot be 0 together, okay? Yeah, so again, this expression is what is under square root. So if you check for smoothness, then you've calculated this part of the integral. Okay, so now you go ahead and find the length. So integral from a to b, just kind of copy down the formula. Okay, plug in. This is equal to the integral from 0 to 2 pi of the square root of, we have that, and it is a squared. Do not calculate again, dt. The integrand is a constant, thankfully. Square root of a squared is just a. It's not absolute value of a because a is positive. Okay, the integral of a with respect to t is at. It's not 1/2 a squared, guys. That would be wrong. Integration is with respect to t, meaning a is constant. A is just radius, constant. And that's not at, that's at. T goes from 0 to 2 pi. And that gives us a times 2 pi. Okay, 2 pi minus 0. Or 2 pi a unit of length. Which is exactly the circumference of a circle of radius a. Circumference is 2 times pi times radius, and that's exactly what we have, 2 pi r.
Professor, just to clarify, you said since we're integrating with respect to t, a is just a constant.
Yes, it is, yeah.
Okay.
A is the radius of the circle. I mean, radius, imagine it's 5, right? The integral of 5 with respect to t is 5t. Okay. Yeah. So if you don't know where circumference of a circle comes from, this is a proof of that. All right. You can also try and do this non-parametrically, but you have to go back to Math 7 and look at the non-parametric version of arc length. Okay. Any other questions here, guys? All right, so C here is defined by t minus sine t, hold on, x is defined by t minus sine t. I'm trying to remember this problem, actually. I don't have it in front of me. I hope it is correct. And I think y is 1 minus cosine t. And t goes from, let's say, 0 to 2 pi again. Okay, I believe these equations result in a cycloid. Don't ask me to graph this. It's not that easy to graph because eliminating the parameter here, guys, is not easy. It's not. Because here I have a t. This is not a trigonometric term. I cannot use a nice relationship between sine and cosine because of this t is on the way. But this is a cycloid. The graph of a cycloid looks like that. Okay, a cycloid is traced by a moving circle, by a point on a moving circle. Okay, so imagine the circle is moving from left to right. That point, imagine that point traveling in the two-dimensional space. As it travels, it generates this curve. So later that point is right there, and then that point is here. If the circle is here, the point is right there. You know, that's a cycloid. Anyway, you don't need to know how to graph this. Yeah, well, if you're asked to find arc length, you do not need to eliminate parameter. Just go ahead and find arc length. I was just telling you guys what this graph is in case you're curious, okay? You can always use Wolfram Alpha to graph this. It should look like that, if I'm not mistaken. Hopefully, I'm not. And we want to find the length, of course. Yeah, so I think this generates just one cycle of the cycloid. All right, this problem is probably in your book, section 10.1. Not this problem, but the graph of C, I believe, is in there. Okay, so let's, by the way, here I will be telling you assume C is simple. Okay, so if you were to note the graph again, this would be the graph. At no time it intersects itself or overlaps, but I will give you that assumption. So you need to check for smoothness. Okay, dx dt, find dx dt, or you can call that x dot if you feel lazy, that's fine with me. That's 1 minus cosine t, the derivative of that. And then the derivative of that is 0 minus negative sine t. So just sine of t. Okay. Yeah. So again, our requirements for smoothness. Those are both defined. Here, I'll just go lazy here. X dot and y dot are both defined. Okay, because they consist of sine and cosine. And again, those are continuous functions. Their domain is all reals. They're never undefined. We don't have a fraction, or we don't have a weird trig function like tangent or cotangent. Okay, so let's check. The second requirement, which means that you have to add the square of those. Okay, so we take 1 minus cosine t squared plus sine t squared. Okay, square 1 minus cosine t, that gives us 1 minus 2 cosine t plus cosine square t. And then here we have sine square t. All right, we have cosine square t plus sine square t right here. And that is just 1. Right, guys? That's 1. Combine that 1 with this 1. And the sum of the square of the derivatives become 2 minus 2 cosine t. All right. Excuse me. And we want to show that this thing is never 0. Okay? And this is the moment where you have to remember your trigonometric graphs. Okay? 2 minus 2 cosine t. But first, you don't need to think too much, okay? You really don't. Just know that the amplitude here is 2. Okay, and so without this 2, the maximum and the minimum are -2 and 2. Okay, but when you add 2, it shifts the graph up by 2. So now the graph is going to be between 0 and 4. Okay, between 0 and 4, including 0 and 4. Here is the graph, in case you're curious. So that's pi over 2, pi, 3 pi over 2, 2 pi. Okay, we have a -2 cosine t. This is reflected around around the horizontal axis. So yeah, so we get like, assume this is 2, -2, and this is 2. Okay, so graph is going to look like that. Now, when you shift this up by 2, it's as if the horizontal axis moved here. Okay, so you get let me do that again. Yeah, so that point goes here, here. Let me just erase that. Right. This is what the graph is going to be. Okay, just picture it in your head. You don't have to graph that cosine wave. So the graph does meet 0. This thing can be 0. All right. But guys, let's go back. So on the closed interval, 0 to 2 pi, we have zeros. Okay, this thing is going to be between 0 and 4. But if you look at the requirement for arc length, let's look at it again. It says C has to be smooth on the open interval AB, not closed, open. So if I exclude the endpoints 0 and 2 pi, if you don't include those endpoints, then the graph is never going to be 0. This is going to be positive for t between 0 and 2 pi, excluding 0 and 2 pi. Okay, so let me write that note down. Two minus 2 cosine t is between 0 and 4. For t between 0 and 2 pi, including those endpoints. Okay, but 2 minus 2 cosine t is between 0 and 4, excluding 0 and 4, for t between 0 and 2 pi, excluding 0 and 2 pi. And that's what we want. Okay, this derivative, the sum square of the derivative is positive. It's between 0 and 4, meaning that it's positive if you exclude the endpoints. And again, the arc length theorem says that the sum square of the derivatives, or C, has to be smooth on open A, open B. Else we would be in trouble. This problem wouldn't work. Okay. Now you can go ahead and find arc length. Pre-calculus. Okay, so from 0 to 2 pi is the length that we want. And we have here square root of, we've already found x dot squared plus y dot squared. It is 2 minus 2 cosine t. All right. So you thought this is an issue? This integral, guys. The thing with arc length, when you find arc length, the integration is almost impossible for every problem. There are a few problems where you can evaluate the integral. Okay, so I would say for every one problem that whose arc length integral you can evaluate, there are infinitely many problems whose integral you can't evaluate. Yeah. And that's a fact because of the square root. The square root is not fun. Okay. Question is, how do we find this integral? All right. And yeah, you can't just say this is 2 minus 2 cosine t to the power of half and add 1 to the power of half divided by the new power. We cannot use power rule. We can't. This is a composite integrand. You have a function within another function. So no basic method can be used, to be honest with you. Okay, so next thing is substitution. Question is, can we use substitution? And the answer is definitely not, because if this is the inner function, because you have the square root of 2 minus 2 cosine t, if you let this be u, the derivative of it is not in the integrand. There is nothing for du that you can use. So substitution doesn't work. Okay. Next method is integration by parts, and you definitely want to forget about that. We don't have parts. This is really a composite thing. You don't have like square root of t times cosine t. We don't have parts. There is only just one part. And that's it. What are you gonna do next? Partial fraction? Come on, that's stupid. We don't have a rational function. What we have here, guys, is some sort of a trigonometric integral. Okay. And there is a trick to be used for this integral. I have to really a root substitution. So root substitution wouldn't work either, because again, if you let u squared equal to 2 minus 2 cosine t, Jose, then 2u du is 2 sine t, and we don't have sine t sitting in the integrand. Basic substitution doesn't work. Root substitution here doesn't work. None of those substitutions work. They don't. All right. This goes back to, did I do the power reduction? Yes, we did the power reduction identities, guys. Remember the power reduction identities? Let's talk about that here quickly. One of the power reduction identities that we used was sine squared t being equal to 1 minus cosine of 2t divided by 2. So I hope you guys do remember this from section 7.2, trigonometric integrals. Yeah. If you notice, this numerator has a 1 minus cosine of something, 1 minus cosine 2t. In this integrand, under the square root, we have a 2 minus 2 cosine t. If you factor the 2 out, we could do that. We end up with a 1 minus cosine of t, which in some ways matches that right here. Okay, I just have to make this 2t a t by replacing t with t over 2. If I replace this t with t over 2, the 2's cancel out, and I get 1 minus cosine t, which is, again, right there. It's right there in front of you. And if you could express that in terms of sine squared, you take the square root of sine squared, that gives you a nice sine, and the integral of sine, we all know what that is equal to. So we have to use this identity to solve that integral. Whenever you see a 1 minus cosine t within an integral, at some point you can use power reduction identities. All right, so let me factor the 2 out from within the square root. We get 2 times 1 minus cosine t. Okay, so again, I look over here. I wish to make this a t. So what I do is I replace this t with t over 2. Here's a different color. So that t, replace t with t over 2, you get sine squared of t over 2 equal to one minus cosine of 2 times t over 2. Okay, that is the argument of cosine all over 2. So here what we get is sine squared of t over 2, that is the argument of sine, is equal to 1 minus cosine of t over 2. And again, that goes over here. All right, so if I solve this for 1 minus cosine t, we get 2 sine squared of t over 2 equal to 1 minus cosine t. 1 minus cosine t and 2 sine squared t over 2 are the same things. Okay, so substitute that for that 1 minus cosine t. So we got that 2 along with the 2 sine squared of t over 2. Yeah, never seen this integral before in chapter 7, but that's what math 8 is all about, integration. Not all of it, but most of it, or for the most part. Okay, so let's take care of this thing here. We have 2 times 2, which is 4. We have the square root of 4, and that is equal to 2. You can move the 2 out of the integral, out of the square root and out of the integral if you want. And then we have here a square root of sine squared of whatever, theta. Okay, square root of a square, guys, doesn't just cancel. The square root and the square don't just cancel out. Remember, we always get absolute value of sine of t over 2 in this case. Okay. So again, justification is that square root of u squared is absolute value of u. Some people might just say that is equal to sine of t over 2, being careless, and get it right by luck. Yeah. So the question is, what do we do with that absolute value? Should we keep it? It all depends on the sign of sine of t over 2, whether this is positive or negative. So what do you guys think? Is this positive or negative on 0 to 2 pi?
Positive. Positive.
It is positive. And why is that? Because sine, the sine function, guys, on 0 to 2 pi, it looks like that. That's one cycle of the sine theta on 0 to 2 pi. So sine is sometimes positive, sometimes negative. But here we have a t over 2. What does that do to the graph?
It just limits it to where sine's gonna be positive.
Yes.
Zero.
Yeah. Yes. So this t over 2 does limit sine to where it's only positive. Because you're going to get only this cycle, only this part of the sine function. So you could just drop the absolute value, basically. Okay. Yeah. So again, let me see if I could. All right. I will write the reasoning for that in the end. Okay. So for now, just believe it if you didn't understand what I said. Now we want to integrate this thing. Okay. And this is just a simple substitution. Or you can use the shortcut that I discussed much earlier in the semester. The shortcut is that if you have the integral of sine of some number, okay, the integral is just 1 over a cosine of at. The antiderivative of sine is negative cosine plus some constant. Okay, so this is by substitution. This 1 over a is by substitution. If you let u equal to at, you get 1 over a du equal to dt. Okay, shortcut. Here your a is 1/2. A is 1/2, so that antiderivative is with the 2 in front. We get 1 over 1/2 cosine of t over 2. Okay, and again, it's a negative. And you're going to vary t from 0 to 2 pi. Okay. That gives us -4. Right, 2 times half is 4. And then plug in 2 pi. You get cosine of 2 pi over 2 minus cosine of 0. So cosine of pi, that is -1. And then we have minus cosine 0, 1. That's equal to -2. -2 times -4 is just 8 unit of length. And that's the answer. Okay. Yeah, so Ahmed is asking, what if sine of t is both positive and negative? Then you have to break up your integral. Ahmed, we have to break it up into 2 integrals. Yeah, so let me write the justification for this step to this step. Okay. Yeah, so here you can go with the period if you like. if we have y equal to sine of t over 2, let's just say the period we call the period t. T is always 2 pi divided by omega. Omega is the number in front of the variable of sine. And that number is again half. Over here, let me write that in a different color. Okay, so do 2 pi divided by 1/2, and that gives you 4 pi. So 4 pi is the duration of one cycle of this sine function, sine of t over 2. Okay, so if you graph now sine of t over 2, one cycle is going to be from 0 to 4 pi. So we're going to have pi, the key points pi, 2 pi, 3 pi, 4 pi, and this is what the sine function would look like. Okay, one cycle is from 0 to 4 pi. From 0 to 2 pi, the piece is positive. It is above. It's above the x-axis or the horizontal axis. Sine of t over 2 is greater or equal than 0 for t between 0 and 2 pi. Okay, therefore, absolute value of sine of t over 2 is just equal to sine of t over 2. You just drop the absolute value. Ahmed is asking, what if the function is both positive and negative? You go back to math 7, Ahmed. I'm just joking. I'll do it for you. This is off topic. Okay, guys, I'm just answering Ahmed's question over here. So Ahmed is asking something like this. What if we were to integrate, let's just say, from 0 to 4 pi of absolute value of sine of t over 2? First of all, the integral would be 0, Ahmed. But actually, no, it wouldn't be. If you're integrating just sine of t over 2, it would be 0. But with absolute value, yeah, so from 0 to 4 pi, sine is sometimes positive, sometimes negative. Okay, you would have to break up the integral. You do the integral from 0 to 2 pi of sine of t over 2. Okay, add that to the integral of from 2 pi to 4 pi. Now, since here sine is below the x-axis, it's negative, you have to multiply it by another negative. Absolute value of sine of t over 2 becomes negative of sine of t over 2. That's how you do it. You break it up like that. Does that make sense, Ahmed? That's not what we want, though. That's not what we were doing. We're just focusing on 0 to 2 pi. This question has everything in it. Just an interesting question. But it's something you're supposed to know how to do. Because we have all the tools, right? Yeah, make sure you guys do the homework for arc length. And make sure you don't skip over those integrals. Do those integrals like twice, 3 times each in the book. Okay, so there is something else in this section. Last topic in section 10.2, right? And it is called surface area of revolution. And this is something you do need for Math 11 or differential geometry, and I kind of have to go over it. So let's start a new page. Last topic. Yeah, this is new. Unlike arc length, that was supposedly done in Calculus 1. This is a new topic, and it has to do with area, not length. Okay, and we are not looking at the area under a curve. That was Calculus 1, where you just do integral of the function. This is something totally different.
Professor, this is still 10 point.
This is still 10.2.
Okay.
It's a never-ending section, man. Yeah, all right. So what is surface area of revolution? Assume that we have some curve, okay? This is C. Now, this C could be parametric, it could be non-parametric. I can derive the non-parametric version of it, and then we just introduce dt later. But assume we have this curve, and it goes from, like, let's say A to B, x goes from A to B. And let's say that this curve is revolved around the x-axis. We could also revolve it around the y-axis, but assume it's revolved around the x-axis. So we get something like that. This is just a reflection. And what it does is that it creates a surface. Okay, it doesn't create a solid, guys. Don't confuse this with volume. For volume, in Calculus 1, you didn't really take the curve to revolve. You took the region bounded by the curve and some axis. You revolve that region around, and that creates a solid. Okay, a three-dimensional object. But here we are just taking that and we are revolving it around. Nothing in between. We don't care about that. This is just empty, okay? When that goes around, again, it creates a surface. All right? Not a solid. For example, if you take a semicircle and revolve it around, it is going to create a sphere. Okay? A sphere. A sphere is empty. There is nothing in there. If you take a semi-disc, revolve that around, it's going to create a ball. A ball, not a sphere. The surface of a ball is a sphere. You guys understand what's going on here, guys? Yeah. Surface versus a solid. Surface is generated by revolving a curve.
Okay, so just quickly, the
Yeah.
difference is that we're not filling it in before revolving it.
Exactly, yeah.
Okay, perfect. Thank you.
Yeah, so again, question is, you have a circle, revolve that around, it creates a sphere. You want to find the surface area of the sphere, not the volume of the ball. Okay, we're calculating a two-dimensional value. Just the surface, not the volume. So here again, the arc of a curve is revolved to generate a surface. It's a surface of revolution, not just any surface. And we want to find the area of that surface, okay? And we're going to call the area here capital S. Little s was used for length, arc length. Big S is for surface area. Okay. So there is some geometry that goes into the derivation of the formula for surface area. What we do is just like what we did for arc length. We are going to take a tiny increment of the surface. Okay, just a tiny, again, you zoom in long enough so that you see a segment. All right, no curvature to it, let's just say. All right, and remember that we call this delta S. Delta little s. Little s is arc length. Okay, so again, going back to the arc length derivation, same thing, okay, same delta s as before. An increment of length is delta little s. Okay, so now imagine you take this increment gets revolved around along with everything else. Let's revolve that around. I'll just do my best. Okay, so when that is revolved around, it creates this two-dimensional object. Well, not two-dimensional object. It also creates a surface right there. Let me just shape I'll just shape the surface here for you, because I want to kill time, I guess. I'm not doing that, sorry. All right. Yeah, this object here, guys, is I could never pronounce the name. I could never. It's called a first of a cone. Okay, it's just a cross section of a cone. Let me draw it. And then I will write the name down. Let me exaggerate also. So here we go. We have that delta S. I really suck at drawing. Okay, so I am a little bit exaggerating, okay? I'm making that a little bigger, if you don't mind. This is delta S. That's called the slanted height. But this is called, again, a first of a cone. Okay, imagine we have a cone. Here's a cone. Let's say the cone is like that. That's a cone. Just take a cross section of a cone. Okay, that cross section is called again first of a cone. All right. Yeah. This thing has dimensions. We have this dimension. This is called a slanted height. Okay. I'll write it down. Delta S is slanted height. Okay, and then we have this upper circle and this lower circle. Okay, the radius of the, and we have the center. Let's say this is the center. Okay, we have the smaller radius, call that R1, and we have the larger radius. We call that R2. Okay, base radii, I guess if you want to call them. All right, and from geometry, we can, I'm not going to prove it, but from geometry, the surface area of this object is, call it A for area. It is 2 pi. Maybe someone, if you're really curious, you could look at y. This is the formula. It is 2 pi times the average radii times the slanted height. Okay, that's a formula for area of that thing. You can look in the back of the book. In the back of the book and the cover page, inside the cover page, there are formulas. I believe this is also included. Okay, so if we plug in, we get 2 pi, the average radii here, just average the two radius, do R1 plus R2 divided by 2 times the slanted height. In this case, we'll just call that delta S, slanted height. Okay, these twos cancel out. And area here is just R1 pi times R1 plus R2 times delta S. Okay, I'm not sure if you take geometry, I'm not sure if they derive this formula. I don't think so. But you can probably derive it if you want. Okay. Anyway, so what does this have to do with the actual surface area of revolution? Well, let's see if we can derive the integral in the 4 or 3 minutes that we have. I'll do my best. Okay, so again, let's say this is the curve revolved, and we have that first one. All right, and let's say this is over some interval from A to B. Okay, this is the x-axis. And guys, I'm doing the non-parametric form of it. Later, we'll make it parametric, as I said before. So how do you do anything that has to do with area, volume, length using calculus? You have to partition. We partition the interval from A to B. All right, and then we'll find individual areas or volumes, and then we add those all up. We'll take the number of partitions to infinity, and that gives you the quantity you're looking for. Okay, partitioning. So how do you partition? You break up the interval a to b into little tinier intervals, right? So for example, this would be like x0, a would be x0, then we have like, let's say x1, x2, and so on. Let me actually make this a little bigger, this graph. I'll make it a little bigger so I can fit the partitions. Yeah, so again, this is x0, we have x1, x2, and so on. Okay, just imagine over this interval, okay, from here to here, we have the kth partition. Okay, call this the kth interval. This is the first interval, second interval, third interval. Imagine this is the kth interval. So this endpoint would be x sub k minus 1. This endpoint is x sub k. Okay, and we are going to take a sample point in that kth interval. Call the sample point, the book calls it, I believe, if I remember from Calc 1, they call it x star. X star sub k. It is just a point in the interval xk minus 1 to xk. Okay, so go to the next page. And again, this is delta S right there. So here the surface area of the kth first, this one. We have multiple of them, so we have so many of these, or we have actually k of them. Okay, I'm just focusing on this particular one. Okay, the surface area, I'm gonna call that delta S sub k. Okay, this is the kth surface area, and we're just looking at an increment of area, so I call it delta. This is equal to, by the formula that we just derived, it's 2 pi times the sum of the two radii. Okay, the first radius is this radius. It's the distance from here to here. And for that, you have to find the value of the function at xk minus 1. Okay. The distance from here to here is f of x sub k minus 1. It is the y value. To find the y value, plug the point into the function, and the lower radius is the value of the function at this endpoint. The distance from here to here is f of xk. Okay, times that by the slanted height, delta S sub k. That's little s. Call that the kth. We'll call that the kth slanted height. Okay. Yeah, so as I said, well, let's continue tomorrow. I'm trying to rush through this. I can't. We'll continue tomorrow, guys. I will finish completing, I will complete the derivation tomorrow because we're out of time. But make sure you do at least all the arc length problems in the book, okay? Maybe I could draw a better picture tomorrow, but I'll see you tomorrow.
Thank you, Professor.
Thank you. Thank you, Professor.
Have a good day.
Thank you.